All right, here we go. We'll go through next example problem of circular motion. This problem is pretty much identical to the pumpkin astronaut problem earlier, just different numbers. All right, but the idea here, once again, in the loop-to-loop, the centripetal force was gravity and the normal force. Here, this is going to be gravity. The centripetal force, what's making it go in a circle, is gravity in this case. A satellite of 100 kilograms moves in a circular geosynchronous. This is an important term, geosynchronous. Geosynchronous means it's matched with Earth. It's right above the Earth's equator, and so it's always in the same place in the same time. It's in sync with the Earth. Its period is exactly the same as Earth's rotation, and it's over the Earth's equator. So that's why you don't have to adjust your satellite dish. If you have Dish Network or DirecTV, you just point at one spot, and it's always there, because the satellite's always in the same place over the planet as the Earth rotates. So that's geosynchronous orbit, Earth-like planet, distance h of 2r. The Earth-like surface, the planet has a radius of 7.4 times 10 to the 5th meters, and the satellite moves at a constant speed of v naught. A geosynchronous orbit means that, okay, there we go. All right, determine the speed. Again, to determine the speed equals distance divided by time. Distance is going to be circumference, 2 pi radius of the planet over the period, right? The radius of the planet. So 2 pi is 2 pi. The radius of the planet, 7.4 times 10 to the 5th meters. And the period is in geosynchronous orbit, 86,400 seconds. That's a day. And so now all you have to do is do some math. That's supposed to read 86,000, but it doesn't look like that. It looks like something very different. That's supposed to be an 8. Okay, so let's do some math. 2 pi is 2 pi. 2 second pi symbol. You should use the pi symbol as opposed to 3.14 in your calculators. 2 pi times 7.4 second e fifth. There's the numerator. Divide that by 86,400 seconds, and we get the speed this thing to be. There's this. So the speed equals 53.8 meters per second. Okay, so the speed 53.8 meters per second. V naught. 53.8 meters per second. I'm not drawing a picture of my own because this picture's already drawn for us, and it's much nicer than the one I would draw. All right, what else? Determine the mass of the planet. Okay, again, here we have to go back to this. That is the key point. So the centripetal force, mv squared over r, and this will be the mass of the satellite, right, times the speed of the satellite squared. The radius would be how far it is from the center of the planet. So this radius would be the radius of the Earth plus 2 radii here. So this would be really 3 radius of the Earth up. Okay, equals g m planet m satellite over the radius squared. And again, I shouldn't say this is radius. This is separation, distance from the center of the two objects. So this is really 3r, and this is really 3r, or radius of the Earth. 3 times 10, right? So here the separation of objects you've got the radius of the planet plus the radius of the planet plus a radius there plus a radius there, 3r. So 3 times 7.4 times 10 to the 5th meters is 220. It's actually 2,220,000. Yeah. Yep. So here we go. Now let's see this. What's so cool? The mass of the satellite cancel out. This cancels out one of those. So you get V squared equals G times the mass of the planet over R. The separation between them. And what do we want to know? We want to know the mass of the planet. So we got to bring that over there. So V squared times R divided by G equals the mass of the planet. V squared, we just figured out, was 53.8. Meters per second squared times 3 times 7.4 times 10 to the 5th meters. Right, there's 3 of those. 7.4, 7.4, 7.4. So it's 3 of them. Divided by their universal gravitational constant, 6.67 times 10 to the minus 11 newtons kilograms squared per meter squared. Backwards, meters squared per kilogram squared. Yeah, whatever. Okay, now just arithmetic. 53.8 squared times 3 times 7.4 second e fifth gives you that numerator divided by 6.67 second e negative 11 gives you 9.63. We'll call it 9.63. Mass of the planet. 9.63 times 10 to the 19th kilograms. That's the mass of the planet. Determine the weight of the satellite on the surface of the Earth-like planet. G, M planet, M object over separation squared. Here, if it was on the surface of the planet, its radius is only 1r. So here the radius is a little different. Pay attention to that, right? Be aware, it's not the same r. The separation change if it goes to on the surface. So here is 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times the mass of the planet, 9.63 times 10 to the 19th kilograms. The mass of the object, 100 kilograms, divided by the separation between them squared, 7.4 times 10 to the 5th meters squared. And that will be its weight. So here we go. 6.67, second E, negative 11, times 9.63, second E, 19, times 100, gives you that, divided by 7.4, second E, 5 squared. All right. $1.17. Newtons. And if the radius were somehow magically doubled, what would happen to the weight of the object? Well, again, just understanding the relationships in that equation, very important. Force of gravity equals G m1 m2 over r squared. If you double that, you get 2 squared, you get 1/4. By doubling this, you'll end up with 1/4 of that. So I always say, pretend everything is 1, even though it's not. If you pretend everything is 1, you get 1. If you doubled the radius, kept everything else the same, but doubled the number on bottom from 1 squared to 2 squared, you get 1/4. So what would happen to the weight? It would be 1/4 as big. It would go down it would decrease by a factor of 4. If the radius were doubled and everything else, what would happen to the weight? It would be 1/4 the weight. Instead of being 1.17, it would be that times a quarter. It would be about 1/4, 0.29, 1/4 of that. All right. Hope that makes sense.